Good afternoon, everyone. My name is Arthur. I'm from Huawei Canada, and today I'll be talking about boosting vLLM inference on Huawei NPUs with Ray compiled graphs. So foundation models are getting larger, right? We have 100 billion to trillion parameter models. We want to deploy them with vLLM, but they can't fit in a single node, even with multi-accelerators. With other Ray applications, it's fairly straightforward to use multiple actors to scale to many nodes. But for serving with vLLM specifically, there's complex memory management involved for things like the KV cache, and there's also memory fragmentation problems to deal with over time. Now, in practice, we saw also high latencies when scaling these inference processes with Ray, which made performance unpredictable for our customers. And at the time, there was also limited support for custom accelerator types for if you wanted to tune these inference processes. So over time, we needed this high-performance execution engine, and previously there were no frameworks within Ray for our needs. So we set out with these requirements on the right side. One, it has to have a low latency overhead for execution. Second, it has to support zero-copy tensor transport. And third, it has to provide a unified programming model for both GPU and Huawei's Ascend NPU accelerators. Now, the last one is particularly important because many companies want to bring their own hardware, and they're looking to open source Ray community for a solution. So we introduced a new feature called Ray compiled graphs, formerly known as Ray ADAG in the early stages. The programming model is essentially a static directed graph representing a workflow of tasks. So the idea is we take this graph, we compile it to a streamlined data plane, and then you can perform various optimizations during execution time in the engine itself. For workloads like model inference, it's perfect because you just have two stages of compute. You have the prefill and the decode stage, and it's a well-known technique to disaggregate them for optimizing performance. And furthermore, you can pipeline the model layers across multiple machines to achieve the high scalability. So the old way, without compiled graphs on the left table, so all the communication and data movement has to go through the object store, which gets serialized through the host and can be very slow with many gRPC calls. In fact, we have seen many scenarios in our own deployment and testing where gRPC becomes the bottleneck, right? And in some cases, it can cause the nodes to drop out in the network when the driver head node gets overwhelmed, when the TCP connections start dropping. So with compiled graphs, which is the new solution on the right, it enables many optimizations like zero-copy transport, reusable buffers, shared memory, and caching. And the overhead of execution is also 2 orders of magnitude lower. And the takeaway is by knowing the data flow ahead of time, you can optimize data movement with Ray compiled graphs. Now, when vLLM released their V1 inference engine, Ray compiled graphs became the default distributed backend. So this was foundational work for multi-node inference on the NPU because it made deployments more stable, and we saw latency improve by up to 40%. And I have some benchmarks later to show that. So firstly, on the Ray side, we have some PRs to support different device types beyond CUDA devices. And this PR in particular takes care of the low latency transport using Huawei's collective communication library, HCCL for short. We add compatibility for primitives like send and receive, and also all reduce and broadcast operators. Now, one thing to note here is the initialization still takes place in the actor, And later on, when we introduce RDT, that process is automated. And the next contribution we have on the vLLM side is to enable SPMD for multi-node inference. So what this means is we create a DAG in the build DAG method here. And the core idea is that each pipeline parallel stage contains a tensor parallel group of workers executing in a SPMD fashion. So under the hood, there's more optimizations like GPU communication overlap, caching, and especially during the tensor passing between the pipeline parallel stages. And overall, in our benchmarking, we deployed vLLM on our Ascend accelerators, and we measured token throughput. For the baseline, we compared it against Ray plus multi-process backends. And the red bar shows with the compiled graph backend, we achieve a 20 to 25% higher throughput in inference workloads. But more critically, in the middle graph, we're able to double the pipeline parallel factor, whereas the Ray plus multiprocessing baseline was enabled to serve the model using this configuration. So this gives us more flexibility in model deployment for production. So there were a couple challenges when we extended this support to Ascend NPUs as well as other accelerators. Previously, the code was very tightly coupled to CUDA and CuPy libraries and assumed a GPU execution model. For NPU and other hardware, they have different memory models and also different intrinsics for cross-device stream and event management. Things like synchronization, barriers, and so on. If you don't handle these events correctly on hardware, you try to overlap data and compute operations, it could cause your Ray actors to hang forever, or you get race conditions, which means your tensor output will be incorrect. So our solution was first to generalize the accelerator device context, and secondly, the stream creation API, so that any hardware can implement their own wrapper for these constructs. The more challenging problem we have is related to the life cycle of torch communication groups, where it could get double instantiated in some cases outside of Ray and inside of Ray. So it turns out some frameworks, including vLLM and VRL, initialize their own torch distributed runtime ahead of time and assigned ranks for each worker. Now, the GPU implementation uses CuPy again as the communicator backend in Ray, so effectively avoids this double initialization problem. But for the NPU, we have to use torch as the collective communications backend. So a rank map needed to be added to maintain this consistency between the upper level frameworks and when Ray initializes at the lower level. And RDT, so yesterday there was an AnyScale talk about Ray direct transport. So here's the complete storyline up to this point, and looking ahead as well. At V0, we know compiled graphs are fast, but there were some limitations due to its static graph programming model. For inference, with the pre-fill decode pipeline, there's no problems because it's a relatively fixed data flow pipeline. In other workloads, however, developers need a more flexible and convenient way to express logic and control flow. So with V0.5, with the GPU Objects API, it partially solved this issue, but again, came with the problem of initializing the collective groups manually. Now at V1 with RDT, it effectively solves both issues while preserving the Ray actor semantics, and everything is taken care of under the hood. To wrap up, we hope to implement multi-device support in RDT, similar with compiled graphs. Next, at the transport layer, we also wish to integrate NCCL for tensor communication with other accelerator libraries. And finally, we want to integrate RDT into vLLM inference engine for workloads outside of inference as well, such as post-training in frameworks such as VRL. So that way, the community has even more choices in hardware other than GPUs when they want to run distributed reinforcement learning. So thanks for listening, and I also want to thank the Ray and vLLM communities for their hard work in this collaboration. I can take questions on the side.